G'day all. Most of the labs that you do in your chemistry course will be real labs in the lab, except this year during 2020 when we're social distancing and we'll be working off video. But in general, you'll be working in the laboratory in your campus and learning about chemicals and chemistry. But basically what we're going to try and do for two of the labs is do them online because the syllabus says that we can, and there are quite good ways to do it online, and there are certain affordances of video recording the experiment that are different from the affordances of doing it live. Now, if you had a molecular modeling kit, you could actually do this live. So, it's worth thinking about as a teacher, what are the affordances of doing it live versus doing it on video. But for now, I'm going to work through it on video. Now, there are a number of different video online molecular modeling software solutions. A lot of them are available online. A lot of them then aren't directly online over the web. You download, install and run, etc. There are very well known ones called JMOL, which is on Java, JSMOL, which is on JavaScript, and a whole variety of other potential solutions. Some of them require reasonably sophisticated knowledge of either Java or Python, which is a programming language, to drive them. Others are much simpler. I'm going to use one from PhET. We tend to use a reasonable number of the simulations from PhET because they're good. They work, they are well designed, they're relatively simple. This one arguably is a bit too simple for year 11 and 12 level, so you may want to use one of the more sophisticated ones. But for this purposes of this lab, I didn't want the learning curve of the software to be the main thing we focus on. I wanted the molecular shapes and structures to be the main thing. So we're going to look at mainly inorganic structures of inorganic molecules this time. Inorganic essentially meaning not containing carbon except for things like carbon dioxide and so on. So organic molecules tend to contain carbons linked to each other along with hydrogens and so on, and we're going to do organic molecules in a whole different lab. So to save you staring at this rather dull screen for a minute, I prepared earlier the search PhET build a molecule. That's what the app that we're going to use is called. Download and install. I'm going to install it on my Apple MacBook. For Windows, it's usually pretty seamless. For Apple, there can be some issues. So I thought I would show you on Apple to show you what can happen. But it's basically not a huge hassle. It's about 5 meg. You can see it downloading down here in the corner. So we'll just wait until that downloads. I'm using Chrome, so that's where the downloads live. They are in different places on different computers. Different browsers. This type of file can harm your computer. Do you want to keep it? Yes, I know where it came from and I'm happy with it, so keep. And then I will drag it to the desktop, and you do this on Windows as well, or find it in the downloads folder, double click on it, and this one says build a molecule can't be opened because it's from an unidentified developer. Your security preferences allow installation of only apps from the App Store. This is Apple being awful and deciding that it's going to only allow you to install stuff that you buy from it, basically. So we need to fix that. So let's go OK, go into Apple, go into System Preferences, go into Security and Privacy up there. Go into click the lock to make changes, because this is the area that we're going. Allow apps downloaded from App Store or App Store unidentified developers. Now I could click the lock to make changes to change that setting, but it's probably not a bad setting to have normally. So I'm just going to click open anyway, because now it's saying that particular thing, you're allowed to open it. So I'm going to open it after all. So yes, I'm sure that that's what I want to do. Okay, so I thought I would just show you, because that can be a thing that gets in the way. The other thing is, if you double click on it in Windows, it might ask whether you want to open it with WinRAR or WinZip, one of the unzipping programs. Please don't do that. Open it with Java, And if you don't have Java already installed on your computer, you may need to install Java on your computer. I've got it already on this computer. So those are the kind of technical traps for young players that might stop this from working for you. I'm certainly happy if you give me a yell and discover that it hasn't worked properly. But those are the three things, is basically make sure you've got Java installed, make sure you open that .jar file with Java, and on Mac, you may need to give it permission to open. Okay, so I can basically make molecules, and the model that they've used here is that you've got a little kit down the bottom of different atoms to use, and it started quite simple. As I said, it's probably good for junior secondary, year 10 or so. It might be a little bit oversimple for year 12s, but you can get pretty complicated and sophisticated with it. And there's a couple of other issues with it that I think are worth talking about. And this is one of the things for your lab report for this, is thinking about not only the affordances of visualizations of molecules versus physical models that the students build in the classroom and can feel in their hands, but also the comparative usefulness of some visualizations over others. So you might compare this one with another one, and some of the setbacks. So, you know, it just happens that the particular kit that we've got, and we've got a bunch of kits we can go to, so we can just click across kit 2, kit 3, kit 4, etc. Well, just kit 3 for this one. This particular kit contains an oxygen and 2 hydrogen, so it's fairly obvious that we might want to make a water. So you just drag that molecule up, you grab your hydrogen and stick it to it, and then you grab your other hydrogen and stick it to it as well. Now, one of the issues with this is that it's a straight line, and we know that the water molecule, depending which angle you look at it from, is not a straight line. But what you can do is click the 3D button, and that will give you a 3D model. Now you've got two options. One is a space filling 3D. Space filling essentially shows you where the molecular orbitals are, so where the electrons are orbiting around the atoms. So that's one representation, and this is one of the benefits of the software, is that you've got multiple possible representations that you can use to get the students really good at mentally switching across. So we had the diagram, now we've got the space filling, and we can just flick to the ball and stick, which is probably we're more used to. We've got the hydrogens out there. We now know that it is a bent molecule. You can rotate it manually with your mouse, so you can have a look at it from whatever angle. This is obviously a very simple one. We'll look at some more complicated ones later. And you can close that. If you messed up and you want to start again, you can explode it using that little explode thingy, and you've just got your molecules separate, your atoms separate, and you can join them back into your molecule. And it's kind of got a tutorial focus to it, so you can actually then pop it up there and it will tell you that you've got it right. So it was happy that I'd got it right. I need to probably go to kit 2 to make O2, because I only had one oxygen in kit 1. So let's go to kit number 2. And I've got 2 oxygens, so I'm just going to make an oxygen molecule. So again, if I just join them together, I get my O2. That is potentially deceptive because, I mean, it is straight. The O2 molecule is linear. But if we get the 3D, we get the space filling. It shows the 2 with their molecular orbitals with the electrons overlapping. If we do the ball and stick, it shows us that it's a double bond, that the OO is a double bond. So does that make sense? So again, we can just close that representation and put it in the box. H2, while we're here, we can make an H2. And the benefit is we can show that in 3D and ball and stick, and it shows that it's a single bond, whereas the O2 is a double bond. So we will quickly move that as well. Now we're also asked to make an N2, but we don't have any nitrogen, so let's go to kit number 3. Let's do the N2 first, because it logically follows. So certainly you should be playing with this and thinking about how you'll get your students to play with it. So the N2, if we do the 3D, again, space filling model, ball and stick model, it will show that it's a triple bond. So we've got a single bond in the hydrogen, we've got a double bond in the oxygen, and we've got a triple bond in the nitrogen. And you can think about why that's the case. So we will drag that into its box, and then we'll do a carbon dioxide. So fortuitously, we've got the right ingredients left to make a carbon dioxide. So let me try and make it wrong first. So if I make it like that, it doesn't allow me to have the 3D model because that's not correct. It doesn't give me a big error warning. There might even be a species like that that could exist, although it would have some weird charge distributions and so on. It's very unlikely. But what it wants me to do is explode it and get it right, which is to put the oxygens on either side of the carbon. So now it's a carbon monoxide because I've only got one oxygen on it. Now it's a carbon dioxide because I've got two. And again, an affordance of this is that it will name the molecules as you make them straight away. So I can have a look at the 3D of that. You can predict in your head whether it's double bonded or single bonded. And it turns out that it's double bonded and it's a linear molecule. Remember that the water molecule was bent, H2O. The reason it's bent is valence shell electron pair repulsion theory, VSEPR, which I don't know whether we get into in year 11 and 12 now or not. I'll have to just double check the syllabus on that one. But that explains why, because those two bonds are repelled by other valence shell electrons on the water. So again, we'll drag that across and we've kind of completed the first and simplest collection. Now we can go to a more complicated one. So we just had carbon, hydrogen, oxygen, nitrogen initially. Now we've got some silicon. So we can make, we could make an N2, but we can't make it with this kit. We could make an H2. We can do that with this kit. So let's make what we can with the kits that we've got. We've already made an H2, so we don't need to have a look at that in the model. And we can make a silane. A silane is like a methane, but has silicon in the middle instead of carbon. Oops, no, I can't make a silane because I'm being silly. I don't have enough hydrogens available to do that. So I'm going to have to... Why don't I go to a kit with a molecule up? No, I can't. Okay. So to make the... Oh, I know what I've done. That's actually interesting, isn't it? So I made my hydrogen. Oh, hang on, let's go back. I can refill the kit. So I can start again. Now, I shouldn't have made an H2 because the H2 was supposed to come from, to be on a different screen. Now, again, that's potentially a problem with the program, but it's something the students might have to figure out. But now I have enough hydrogens to make the silane because I didn't use any of them in an H2. So there's some interesting sort of problem solving and thinking around this. Now, one of the things that the syllabus asks us to look at is different kinds of atomic structures. So we've looked at linear, we've looked at bent, we haven't looked at trigonal planar, where you get three bonds heading out in the directions of a plane. This is a tetrahedral structure. So it's actually in a kind of a three-pointed pyramid structure, where you've got basically what's happening is the silicon's in the middle, all the hydrogens are on the surface and they want to be as far away from each other as they can. So the way that they can get the most distance from each other is by distributing themselves in this orthogonal pyramidal, what's the word I'm looking for? Tetrahedral structure. Okay, so there's my silane. It's basically, as I say, an analog of methane that has a silicon instead of a carbon in the middle. We'll get to methane a little bit later when we... Okay, so boron tetrafluoroborane, or sorry, trifluoroborane. So a boron in the middle and three fluorines around it. Will it allow me to put them on an angle? No, probably not. Again, that's one of the interesting... Now I'm predicting that the structure of this is going to be trigonal planar, trigonal. It's going to be flat rather than that tetrahedral structure and rather than a straight line. I could be wrong, but that's my prediction, is that because the fluorines similarly are trying to get as far away from each other as they can, but there's only three of them, not four. So it turns out that distributing themselves around the equator at the greatest distance will give them the maximum separation. So It looks pretty good from the space filling model. Ball and stick model will nail it down, but yes, that's a trigonal planar structure. And again, you can rotate it and play with it, and we'll pop that in the relevant box to get our tick. Kit number 3 has 2 hydrogens, so we can make an H2, but we've kind of already made one, so let's just ignore that. Kit number 4 has 2 nitrogens, so we can make an N2. Kit number 5 has all the nitrogens, so let's make the nitrogen N2 with this one, because kit number 4 had 2 nitrogens but an oxygen as well, and I think we have to make an oxide of nitrogen down the bottom there. So we'll put our N2 in, and then we'll go to kit 4. I'm not going to belabor this enormously. Now N2O, nitrous oxide, I'm not 100% sure off the top of my head about the structure, but by an analogy with the water, what happens if we put the oxygen in the middle? It doesn't look happy with that. So let's explode it and have another go. We put the 2 nitrogens together and an oxygen. There's nitric oxide. There's nitrous oxide. That's the one we were looking for. So the structure of that is going to be interesting to have a look at. We've got 2 nitrogens and an oxygen. The space filling model is interesting because it shows us how the electrons are distributed, and then the ball and stick. It is a linear structure. You've got a triple bond going to a single bond. The space filling is actually kind of telling you that because this bit's fatter, so there's more electron density up that end and less electron density up this end, but the detail is in there where you've got this sort of triple bond to a single bond. So we'll drag that to its section as well, and we've completed the second collection, and we can continue. So there is some borane and a whole bunch of others. Let's do a methane, a CH4, because there is one more shape that we need to do. And I don't know whether this is going to do it for us or not. I suspect this is going to be just like the silane, and it's going to be tetrahedral. But I would really like it to be pyramidal, but no, it's just another tetrahedral shape. So as I said it was going to be, it's very similar to the silane, except it's got a carbon in the middle instead of the hydrogen. Now let me so there are obviously quite a few options. Actually the options are just resets. There's not a lot of options. I meant to say there are quite a few tabs that you can do. So you can create our goal. This is, again, you can use this sort of game like for younger students in particular. Our goal is to make 2 CO2s. Well, we can't make 2 CO2s with this kit because we've got no carbons. So we have to find what we've got, and then we have to make 2 carbon dioxide molecules. We remember that they had the oxygens on each side. We can make another one, and we can drag one, and then we have to drag another because we need 2 in total, and then we get our ding of approval, and so on. So there's a number of things there. And then larger and more complex molecules, they've kind of left it fairly open. There's no specific task, but we could, if enough time was allowed, make something. Let's actually just make something pretty simple, but we might make a propane, and then I'm going to wrap this video up and release you to go play with Build a Molecule on the PhET site. As I did, just Google PhET, P-H-E-T, and Build a Molecule, and you'll get to this thing. And you can think about the various kinds of structures that we've got. So what it does, again, is identify those things immediately. This is normal propane. It's just a straight three carbon sequence. If we turn it into an oxygen, into an alcohol, sorry, whoops, I'm going to have to explode it completely. I can't just pull one off. So let me explode it. Let me actually throw in an oxygen. So what am I going to make? You guys know your chemistry. I'm going to make some, well, make your prediction, because it's a predict, observe, explain. It's going to tell us what we've made when we assemble it. It might make some guesses. Prop 1-ene 1-ol is assuming that there's a double bond here, which is why there's no hydrogen. So that's what's going on then. And again, we will look at organic molecules in a different video. But this is propan 1-ol. It's a propanol. It's a propane that's turned into the alcohol propanol, and the alcohol functional group is on atom number 1. I better stop because I'm getting very much into organic chemistry structure. But there's a lot of things you can build with the various kits in this stage. There's a lot of various elements that you've got that you can play with as well. So I hope that's a useful and interesting video. Your lab report, basically, as I say, is about how you built, what you did, whether perhaps you tried some of the other molecular construction software that's available on the web as well, of varying degrees of sophistication and complexity, and then about the teaching. How would you teach with this? What are the good bits about teaching with visualization versus teaching in the classroom? Would you complement both things, get them to do physical models and also this? Are there problems with this that you would like to see fixed, the way that the structures are represented and so on, and so on. So I hope that's helpful and interesting, and I will see you next week.